Welcome to our presentation on collision theory and transition state theory. These are the foundational concepts of chemical kinetics that explain why chemical reactions occur at different rates. Every chemical reaction requires molecules to collide with enough energy and the right orientation. At the peak of the energy barrier lies a fleeting species called the transition state. In this presentation, we will explore the requirements for effective collisions, the Arrhenius equation, potential energy surfaces, and the Eyring equation. We will also test your knowledge with quizzes and work through detailed problem solutions. By the end, you will understand what controls the speed and outcome of chemical reactions at the molecular level. Collision theory was developed by Max Trotz and William Lewis in the early 20th century. It states that chemical reactions occur when reactant molecules collide with each other. However, not every collision leads to a reaction. Only a tiny fraction of collisions are effective. The rate of a reaction depends on three key factors: the collision frequency, how often molecules bump into each other, the fraction of collisions with sufficient energy to overcome the activation barrier, and the fraction of collisions with the correct geometric orientation. The fundamental equation of collision theory for a bimolecular gas phase reaction between A and B is rate equals Z subscript AB times F times P. Here, Z subscript AB is the collision frequency, F is the Boltzmann factor, e to the negative EA over RT, and P is the steric factor accounting for orientation. Three conditions must be satisfied for a molecular collision to result in a chemical reaction. First, the molecules must collide with sufficient kinetic energy to overcome the activation energy barrier. Think of two cars approaching a hill. Only those with enough speed can make it to the top. Second, the molecules must have the correct spatial orientation at the moment of impact. For example, in the reaction of nitrogen dioxide with carbon monoxide, the nitrogen atom must approach the carbon atom. If the oxygen end collides with carbon monoxide, no reaction occurs. Third, the collision must transfer enough energy to break the existing bonds. The steric factor P accounts for all these geometric and dynamic constraints. It ranges from about 1 for simple atoms to as low as 10 to the -6 for complex molecules. Activation energy is the minimum energy that reacting molecules must possess for a reaction to occur. It represents the energy barrier between reactants and products. On a reaction coordinate diagram, activation energy is the energy difference between the reactants and the transition state at the top of the barrier. For an exothermic reaction, the products have lower energy than reactants, but the reaction still requires activation energy to proceed. Thermodynamics tells us if a reaction can occur, but kinetics tells us how fast. A reaction with activation energy of 25 kilojoules per mole proceeds about 5 times 10 to the 21st power faster than one with 250 kilojoules per mole at 300 Kelvin. The Boltzmann distribution tells us that at temperature T, the fraction of molecules with energy at least Ea is e to the negative Ea over RT. Raising the temperature increases this fraction dramatically. The Arrhenius equation, formulated by Svante Arrhenius in 1889, is the central mathematical relationship of chemical kinetics. It connects the rate constant K to the activation energy Ea and temperature T as K equals A times e to the negative Aa over RT. The pre-exponential factor A represents the rate at which collisions occur multiplied by the steric factor. The exponential term gives the fraction of collisions with sufficient energy. Taking the natural logarithm gives the linear form. Log of K equals log of A minus Ea over R times 1 over T. This allows experimental determination of activation energy by measuring K at several temperatures and plotting log of K versus 1 over T. The slope is negative Ea over R and the intercept is log of A. The two-point form is useful when rate constants are known at only 2 temperatures. Transition state theory, also called activated complex theory, was developed by Henry Eyring, Michael Polanyi, and Meredith Evans in the 1930s. It provides a more detailed molecular picture than collision theory. The theory assumes that reactants are in equilibrium with an activated complex, the transition state, which then decomposes to products. The Eyring equation expresses the rate constant in terms of thermodynamic activation parameters. K equals kBT over H times e to the delta S double dagger over R times e to the negative delta H double dagger over RT. Here, Kb is Boltzmann's constant, H is Planck's constant, delta H double dagger is the enthalpy of activation, and delta S double dagger is the entropy of activation. A negative delta S double dagger indicates a more ordered transition state than the reactants, making the reaction slower. Transition state theory is particularly powerful for understanding how catalysts work by stabilizing the transition state and lowering the activation barrier. A potential energy surface is a multidimensional map of a molecule's energy as a function of all atomic coordinates. For a simple reaction like H plus H2 giving H2 plus H, the surface has two coordinates, the two bond distances. The surface topography reveals valleys for reactants and products, peaks for high-energy configurations, and saddle points. The minimum energy path from reactants to products is called the reaction coordinate. The saddle point along this path is the transition state. It is a maximum along the reaction coordinate, but a minimum in all perpendicular directions. This is why the transition state has one imaginary vibrational frequency, the vibration along the reaction coordinate that leads to bond breaking. Modern computational chemistry uses potential energy surface calculations to predict reaction pathways and transition state geometries. The Hammond postulate relates the structure of the transition state to the energy of the reaction. For exothermic reactions, the transition state resembles the reactants, while for endothermic reactions, it resembles the products. Several factors influence how quickly reactions occur, all of which can be understood through collision theory and transition state theory. Increasing temperature raises the average kinetic energy of molecules, shifting the Boltzmann distribution so a larger fraction have energy at least the activation energy. As a rule of thumb, many reactions double in rate for every 10 degrees Celsius increase. Higher concentrations increase collision frequency, directly increasing the rate. For gases, increasing pressure has the same effect as increasing concentration. For heterogeneous reactions involving solids, a larger surface area exposes more reactant particles for collisions. This is why powdered solids react faster than large chunks. Catalysts provide an alternative reaction pathway with a lower activation energy, dramatically accelerating reactions without being consumed. Enzymes are biological catalysts that can accelerate reactions by factors of 10 to the 6th to 10 to the 15th. The presence of a catalyst does not change the equilibrium constant or enthalpy change. It only helps the system reach equilibrium faster. Quiz question 1. According to collision theory, which of the following is not required for a chemical reaction to occur? Option A. The molecules must collide with sufficient energy. Option B. The molecules must collide with proper orientation. Option C. The collision must occur in solution. Option D. The collision frequency must be adequate. Take a moment to think about your answer. The correct answer will be revealed shortly. Quiz question 2. What does the steric factor P in collision theory represent? Option A. The fraction of molecules with energy at least Ea. Option B. The fraction of collisions with proper molecular orientation. Option C. The total number of collisions per second. Option D. The activation energy divided by RT. Think carefully about what each of these represents in the collision theory equation. Quiz question 3. In transition state theory, a large negative delta S double dagger indicates what? Option A, the reaction will be very fast. Option B, the transition state is highly ordered and the reaction is slower. Option C, the activation energy is zero. Option D, the reaction is exothermic. Remember what the entropy of activation tells us about the transition state structure. Quiz question 4. On a potential energy surface, the transition state corresponds to which feature? Option A, the global minimum energy. Option B, the reactant valley. Option C, a saddle point with one imaginary frequency. Option D, the product valley. Consider the mathematical definition of the transition state on a potential energy surface. Quiz question 5. According to the Arrhenius equation, if the temperature is increased from 300 Kelvin to 310 Kelvin for a reaction with activation energy of 50 kilojoules per mole, what happens? Option A, the rate constant approximately doubles. Option B, the rate constant decreases by half. Option C, the activation energy decreases. Option D, the frequency factor A increases. Use the two-point form of the Arrhenius equation to calculate the expected change. Problem 1. Arrhenius calculation. A first-order reaction has an activation energy of 75 kilojoules per mole and a frequency factor A of 2.5 times 10 to the 12th per second. Calculate the rate constant at 298 Kelvin. The gas constant R is 8.314 joules per mole Kelvin. We will work through this step by step. First, we write the Arrhenius equation with known values. Then we calculate the exponent factor EA over RT, which equals 75,000 divided by 8.314 times 298, giving 30.27. Next, we evaluate e to the negative 30.27, which is 2.52 times 10 to the negative 14. Finally, we multiply by the frequency factor to get k equals 6.3 times 10 to the negative 2 per second. Problem 2. Activation energy from rates. The rate constant for a reaction is 4.20 times 10 to the negative 3 per second at 350 Kelvin and 2.10 times 10 to the negative 2 per second at 370 Kelvin. Calculate the activation energy in kilojoules per mole. First, we set up the two-point Arrhenius equation. Second, we calculate the rate constant ratio, which is 5.00 with log of 5.00 equals 1.609. Third, we calculate the temperature term, 1 over 350 minus 1 over 370, giving 1.544 times 10 to the negative 4 per Kelvin. Fourth, we solve for EA, which equals 86.7 kilojoules per mole. Problem 3. Eyring equation calculation. Calculate the rate constant at 310 Kelvin with an enthalpy of activation of 60 kilojoules per mole and an entropy of activation of negative 50 joules per mole Kelvin. Step 1. Write the Eyring equation. Step 2. Calculate the frequency factor kBt over h equals 6.46 times 10 to the 12th per second. Step 3. Calculate the entropy term e to the delta s double dagger over r, which is 2.43 times 10 to the negative 3. Step 4. Calculate the enthalpy term e to the negative delta h double dagger over rt, which is 7.84 times 10 to the negative 11. Step 5. Multiply all factors to get k equals 1.23 per second. Problem 4. Collision frequency and steric factor. For the gas phase reaction of two high molecules producing H2 and I2 at 500 Kelvin, the experimental rate constant is 2.0 times 10 to the negative 6 per molar per second. The collision frequency Z is 3.0 times 10 to the 10th per molar per second. We need to find the steric factor P and activation energy. This problem illustrates an important point. Simple collision theory fails for complex molecular rearrangements. The calculated steric factor comes out greater than 1, which is physically impossible. This tells us that the simple collision model is inadequate for reactions involving complex bond rearrangements. We need transition state theory for an accurate description. Problem 5. Temperature dependence. A reaction with activation energy of 85 kilojoules per mole has a rate constant of 0.00320 per second at 300 Kelvin. At what temperature will the rate constant be 0.0500 per second? We use the two-point Arrhenius equation. The rate ratio is 15.625 with log of 15.625 equals 2.749. Substituting into the equation and solving for T2 gives 326 Kelvin, which is 53 degrees Celsius. A 26 Kelvin increase makes the reaction 15.6 times faster. This demonstrates the strong temperature sensitivity of reactions with moderate activation energies. Let us consolidate everything we have learned about collision theory and transition state theory. Collision theory tells us that reactions occur when molecules collide with sufficient energy and proper orientation. The rate depends on collision frequency, the Boltzmann factor, and the steric factor. The Arrhenius equation quantifies how temperature affects reaction rates through the exponential activation barrier. Transition state theory provides a deeper molecular picture. Reactants form an activated complex at the saddle point of the potential energy surface, which then decomposes to products. The Eyring equation separates enthalpic and entropic contributions to the barrier. Catalysts accelerate reactions by stabilizing the transition state and lowering the activation energy without affecting thermodynamics. Understanding these principles allows chemists to predict reaction rates, design more efficient industrial processes, and develop better catalysts. Key equations to remember include the Arrhenius equation, the Eyring equation, and the relationship between activation energy and the transition state energy.